Aloha, everyone. Let's just give folks another minute or two to arrive before we get started. For those of you who haven't seen yet, I've pinned in the Slack channel a Google Doc where we can focus our discussion a little bit. I've put down a few questions that we might think about for our breakout, and we of course can edit and add to this document as we go today. There's also within that document a link to a slide deck, which a couple people, Andrew Howard and Dimitri Maue, have kindly added some slides. So we'll be able to actually look at some figures and images related to some of the new exoplanet science instruments coming to Keck. So I'll just add the link to that slide deck as well in the Slack channel.
Lauren, do you mind posting those in the Zoom chat, if that's okay? I don't have access to that slide.
Yeah. Okay, so here is the Google Doc. And the slide deck. So does this breakout session officially start now or a few minutes from now? I'm still a little foggy on the schedule.
I think
it's now.
We should sort of be accommodating that people might be grabbing lunch and coming in a little late, but that, you know, we have many time zones here. So Lauren, it's probably early for lunch for you, for example.
Yeah, the coffee is still working. I'm not really quite aware of what time it's supposed to be. Early mornings combined with observing are not a recipe for awareness of time. Okay, but it looks like it's now 1:05 Pacific. So maybe now's a good time to get started for folks dialing in. We have some documents that I've shared in the Slack channel, so you can follow along on those. Maybe I'll share my screen really quickly just so we can all literally be on the same page. Okay, so here's the Google Doc. So I selfishly created this breakout session out of my own desire to have a better understanding of all of the amazing new Keck science instruments coming that will help us do exoplanet science. So the questions that I had are, well, I know there's a lot of new instruments and I know about some of them, but what new instruments are there? And by new, I mean anything from we upgraded near spec and now it can perform X where it used to just perform Y to, you know, to very early sort of design phases of possible future new instruments. Second question is, in what ways are these instruments specifically designed to enhance exoplanet science, right? In addition to, you know, a light path, what I'd really like to know is what does this mean for like the incremental science knowledge that we're going to gain from this instrument? Related to that is how could we use these instruments in combination to tackle novel questions? So each of these instruments is sort of purpose designed for addressing, say, questions A, B, C. But what I'm curious about is, can we together as a group today identify ways to use these instruments in combination to actually do totally new kinds of science? So that's, of course, a very open question and one that I hope we will carry with us beyond this breakout session. And then the last one is, are there alternative sort of creative ways to use these instruments that would benefit exoplanet science? So without further ado, let's jump over to the slide deck. So there are a few slides here, and I think I will actually let a couple of people who volunteered to present share their screens. So we are at the Keck Science meeting, and the three instruments for which people have given me slides are the Keck Planet Finder, which is first light estimated 2822, the Keck Planet Imager and Characterizer, which is currently on Sky, and the high resolution infrared spectrograph for exoplanet characterization, which I don't know, is maybe coming soon. So without further ado, I'm going to hand over screen sharing to Andrew Howard, who will present on the Keck Planet Finder.
Thanks, Lauren. All right. You should be seeing my screen now. All right, so what I want to do is I have 6 slides on the Keck Planet Finder. I'm going to tell you a little bit about the instrument, the kind of progress and status of it. I'll show you what we think the data are going to look like. I want to talk through some of the science cases, and then I want to kind of lay out a little bit of the strategic landscape. The goal of this talk, I think, is mostly just to introduce KPF to the Keck community. We've had other talks about this in the past, but KPF is going to be a real thing soon. And so now is the time for folks to start thinking about how to use it. Okay, so first a little bit of a kind of system level overview. This is a somewhat busy slide that tries to capture the kind of multiple elements that make up KPF. So KPF will be fed by the Keck 1 telescope. We have a fiber injection unit which sits on the AO platform. It does not use AO. There's a little flip mirror that steers the light off to the KPF fiber injection unit. We will use ACAM, that's part of the AO system. The fiber injection unit sends the visible band light, that is 445 to 870 nanometers, down to the basement of Keck Observatory, where in the hallway between Keck 1 and Keck 2, we'll have a thermal enclosure and a vacuum enclosure that houses the core spectrometer for KPF, which is shown on the right. So KPF is a 2-arm sort of classical cross-dispersed white pupil Echelle spectrometer. The 2 arms cover different wavelength regions. A unique design aspect of KPF is that everything which is shown there in tan, most of the optics and the base of KPF are made out of zero-dur glass. This is the same extremely thermally stable material that the Keck telescope primary mirrors are made out of. So we think that one of the major strengths of KPF is that it will be extremely thermomechanically stable, which will minimize systematic errors. A couple other subsystems of KPF which are sort of worth noting. One is that there is a separate calcium H and K spectrometer. So we break off the UV light and monitor those very important lines for calcium for stellar activity. This is a subsystem which is being designed by Ashley Baker, who's a postdoc at Caltech, and now she's on the line. And then there's a number of other kind of small systems, including a laser frequency comb, an Etalon. We have a thing called a scrambler, which optically mixes the modes inside the fibers, and a reformatter. Okay, so in kind of table form, here's what KPF will do. It is a kind of generic optical Echelle spectrometer that has a fixed format. There are no moving parts, and it's highly optimized for Doppler measurements. If you have other ideas of cases where high resolution spectroscopy will be helpful, KPF could still be a great instrument for you. So especially things like transmission spectroscopy, where you need a very stable instrumental profile, or even things like looking for the kind of subtle shoulders on line of stellar lines, looking for abundance and isotopic analyses. KPF will have a single object fiber. It's seeing limited. We also have a sky fiber and a separate calibration fiber. We are one of the first instruments that will serve basically AppJ quality data to users right out of the box. So we have a public data reduction pipeline. It's public in the sense that you'll be able to download the code and use it if you want. If you don't want to do that, your data will appear completely processed in the Keck Observatory archive the next day. We are working on something called Community Cadence, which will be a KPF-specific capability. This is sort of a pseudo queue recreating what has been done for years by the California Planet Search, and it will enable time series measurements over the full calendar year. Lots of details to work out here, and at that, that's still ongoing. Okay, so the exciting thing is KPF is really happening. We're now fully funded. We were recently awarded an MSIP award. It's being assembled starting in January of this year. We've ordered most of the components. The engineering's almost done. First light in the middle of 2022. Okay, let me speed up a little bit here. This is two different views of the optical efficiency of KPF. Looking only at the spectrometer, which is the top panel, you can see that KPF is quite efficient compared to its competition, especially compared to high-res, which is currently on the Keck 1 telescope. If you construct a statistic, which we call survey speed, which is the spectrometer efficiency times the telescope size, KPF is really in a class of its own. Here's what we think the data are going to look like. These are simulated time series measurements of transits of planets. These are so-called Rossiter-McLaughlin measurements, and we measure the shadow of the planet as it goes across different parts of the stellar disk. Now, we chose this kind of measurement as a demonstration because it highlights the fact that it's a combination of the precision of KPF, the efficiency of the instrument, and the aperture of the telescope. On the left is a comparison with the NUID instrument, which is on the 3.5 meter WIN telescope. And on the right, we're showing a comparison with Subaru IRD. This is for an M-dwarf star where IRD really excels. IRD is an infrared spectrograph, but because KPF goes to such red wavelengths out all the way to 870, we're very efficient for M-dwarfs as well. Okay, the science capabilities. So as I mentioned, KPF was really designed for precise Doppler measurements, but it's a general purpose spectrometer, high resolution optical spectrometer. And so we're confident that the community will think of lots of different things. It's going to be a standard facility class instrument that's open to absolutely anyone who's part of the Keck community, which with NASA includes more or less the entire world. We have formed a science team for the purpose of the MSIP award, and the science team is planning to execute the science projects, which are listed on the right. I'd be happy to provide more details if people are interested in these. This construction of the science team is not meant to be exclusionary, and there's no reserved science or guaranteed time associated with the science team. This is simply a mechanism that motivates to the NSF that we can do exciting science, and we have a path to do so. The last slide that I'll show might be for some of the sort of Doppler aficionados in the audience. What's exciting is that we can go really faint with KPF. So if you want to go sort of 1 meter per second photon limited precision, and you're willing to take hour-long exposures, you can get 14th magnitude G stars or something like 16th magnitude M stars. So this is a couple of magnitudes fainter than high res or than any of the precise spectrometers on the 3 and 4 meter class telescopes. And putting all of that together, if you think about how quickly you could do a survey of either G-type stars or M-dwarfs, you can see that KPF excels at both relative to the competition. So that was all that I had. Maybe we should, I don't know, Lauren, I don't know how you want to run this. If pass it on to Dimitri and questions at the end or discussion, but back to you.
Yeah, I think if there are any questions on, I guess, sort of the first 2 bullet points of like what is KPF and what was it designed to do about exoplanet science, maybe Andrew could take those, and we'll reserve questions 3 and 4 for after we've talked about other instruments. Let's see. So are there any questions on what is KPF and what was it designed to do? Okay, then let's go to Dimitri's slides. So Dimitri, are you here?
Yes, I am. Can you show, if you have the slides handy, can you show them for me, please?
Sure, happy to do so.
Thank you.
I'm just pulling them up right now. Okay, so we talked about the Keck Planet Finder. So next up is going to be KPEC.
So there are a lot of people from the KPIC team on the line, and I invite them to speak up. If I say anything stupid, I might call someone in to help with the discussion here. So what is KPIC? KPIC is a suite of upgrades to the existing facilities, mainly the Keck 2 adaptive optics system, and targeted upgrade to NERC2, the workhorse infrared imager of Keck 2, and Spec, which is our only high-res infrared spectrograph at Keck. So I talked about briefly the upgrades to the system that have now been fully commissioned and facilitized and available for science use. So we, when I say we, it's a large group of people involving observatory staff, collaborators at Subaru, Keck, JPL. So we installed a pyramid wavefront sensor using an infrared camera, which is a Saphira array. So it's a very low noise, fast readout infrared camera. And this new wavefront sensor enables adaptive optics on red targets that can't really be done with current visible Sharp-Raman wavefront sensor. So the primary goal of this infrared wavefront sensor is to do adaptive optics imaging and high contrast imaging around red targets such as M dwarfs, and also perhaps more importantly in star forming regions where we are subject to dust extinction. And so we started a survey for protoplanets in protoplanetary disks, mostly characterized by the ALMA array. So we're looking for the thermal emission of forming planets within disk structures such as gaps and cavities. And so this is here an example of an image taken recently of the two protoplanets in the PDS-70 disk. So this is a paper that was recently accepted, and the first author is on the line, is Jason Wang. So if you have more questions about that, feel free to ask Jason. So the pyramid is working well. It is available. The limiting magnitude is around h of 12 or so. So, but that means that you can lock on very red targets easily that you wouldn't be able to do with the Sharp-Raman visible wavefront sensor. So the other part of the KPIC upgrade was the installation of a series of new Vortex Masks inside NERC2 that operate at K, L, and M band, along with an optimized LEO stop. Also, FYI, we installed Wollaston Prism inside NERC2 to enable polarimetry. It's an effort led by Max Miller-Blanchard. I don't know if he's on the line. We are currently working on installing a modulator that would allow us to do disk polarimetry and KNL band polarimetry of any target you wish. So the polarimeter of NERC2 will be soon fully functional. Then I think perhaps more exciting, at least for me, is this new fiber injection unit that has been installed as part of the KPIC facility that links the Keck 2 adaptive optics system to Spec via single mode fibers. So it took us a while to get the system up and running, but now it's really going very well. So we had a series of very successful science nights early July. where we detected a series of low mass companions and exoplanets, including HR 799, C, D, and E. You see here the results of our science verification run, where all 3 planets were detected at our 35,000 in K-band. The plot here shows the equivalent of a cross-correlation function showing that we can see the planets quite rapidly, actually. And so what high-resolution spectroscopy allows us to do for these directly imaged planets is to measure molecular abundances, also do all kinds of Doppler measurements, so we can measure the planet RV directly and its spin. And we have a few nights coming up this semester where we are going to attempt a Doppler imaging experiment on some of these low mass companions. So now the system is up and running. I think we've reached all of our requirements. We have a few upgrades coming next year for the fiber injection unit, which will incorporate additional coronagraphic capabilities, as well as an ADC and a few other gizmos with the goal to improve contrast and efficiency, system efficiency. Any questions?
I have a quick question. So I've been seeing these images, like the PDS-70 image, and they're absolutely fantastic. Congratulations on this awesome update. What I wish I understood a bit better is how much improvement is this over sort of the previous iteration of NIRSpec and NERC2 without KPEC?
Yeah, so in principle, you would be able to do this, same kind of studies and detections for objects that were not accessible to natural gas star AO before. So in particular, if you look at the Taurus or Rho Fucus star-forming regions, that a lot of these targets are too faint in the optical to lock the adaptive optics system on. So now we've opened up a large fraction of these star-forming regions for these kind of studies, and hopefully we'll find more of these protoplanets in the future. That wasn't possible before, and neither GPI nor Sphere can actually look at these systems.
Great, thanks. Are there any other questions about KPEC?
And going to the fiber injection unit, that's the first system that allows us to do high contrast, high spectral resolution studies of these low mass companions. So there's no other system right now that can do the same thing. All right.
Great, thanks. All right, so now we will move on to high spec, if I'm pronouncing it right.
Yes. So sorry for the busy slide. I tried to condense the information in one slide. So high spec is a new instrument that we are currently designing. So this is if you want a super NIRSpec that will be fiber fed. So using the same ideas as what we are doing for KPIC. So we will have a fiber injection unit, which will be similar to the KPIC fiber injection unit. And so inject light from the Keck 2 adaptive optics system into single mode fibers, propagating the light to a new spectrograph that is designed from the ground up to be diffraction limited and fed by these single mode fibers. So we break basically the limitation associated with the beam étendue, and so the spectrograph can be extremely compact, which is what we think is advantageous for Doppler stability. So you see here on the lower right, the spectrograph to scale, and we've decided recently to split the spectrograph into 2 channels, 2 different cryostats, one that covers Y and J, the other one H and K. And so this instrument will allow us to take a spectra from 0.95 micron to 2.45 micron in one shot. So the band pass is quite huge, and everything will be at R 100,000 or so. And And so the advantage of a spectral graph like this, so it's a Doppler machine, but it will enable studies covering all three main techniques in exoplanet science. So transit spectroscopy for closing planets, direct spectroscopy, very similarly to Keck, for planets further out, and then discovery and masses with infrared PRVs for objects that are either too red or too young to do with KPF. And there's going to be a great synergy with KPF because now we expand the wavelength range for RV studies by basically 1 octave, 1 full octave. So the design for high spec is inherited from a Pathfinder instrument currently operating on a 200-inch Hale telescope at Palomar Observatory called PARV. And so our main focus will be on exoplanets, but this instrument can also do many other things, star and planet formations, solar system studies, stellar astrophysics, galactic center, and extragalactic science as well. So our goal is to provide an instrumental stability at the level of about 30 centimeters per second. And the end-to-end efficiency should be around 5% or more. It will increase towards the red wavelength. So we are here limited by the performance of the adaptive optics system. So the end-to-end efficiency of a diffraction limited fiber-fed spectrograph is really mostly driven by the performance of the adaptive optics system. And so as we improve the adaptive optics system, so will our end-to-end throughput. So the point source sensitivity for the baseline design is around 14, 15 magnitudes. So that's for SNR 30 for a resolution element in 1 hour. So this is across the Y to K wavelength range. So we'll have several modes. We'll have a single object mode for classical spectroscopy, RV studies, transit spectroscopy. We'll have a high contrast off-axis mode, which will allow us to target off-axis companions, just like Keck. And then we have a very special mode, which is a brand new technique called the Vortex fiber nulling, which I'm very excited about, which will allow us to do detections, not just characterization of very close-in planets right in between the transit regime and the direct spectroscopic regime. So this vortex fiber nulling mode will open up a region with an inner working angle of around 0.5 lambda over d, so half the diffraction limit, which no other coronagraphic technique can do. So we really bridge the gap between close-in companions that can be done with transit and non-transiting emission techniques, and the direct, well-resolved off-axis companions. So we basically cover pretty much all of the parameter space that you can see in the upper right plot there. So we are working on the instrument design and the proposal. We are hoping to submit a proposal to fund the instrument build in the next few months. And there's a poster, there was a poster this morning, there's another poster session tomorrow. If you have more questions about the design and the science, feel free to join tomorrow as well.
Great, that's fantastic. Thank you so much, Dimitri. Are there any questions about the technical aspects of high spec or what it's designed to do? I actually have a quick question, which is that you say the point source sensitivity was 14 to 15 magnitudes. In which band is that?
Oh, this is, so 14 is at the blue end of Y band and 15 is at the red end of K band.
Great, thanks.
And the reason why it's more sensitive in the red is because the AO system works better in the red.
Got it. That makes sense. All right, so let's, I'll leave the slides up so that we can refer to them if need be. But for now, let's open up the discussion to sort of broader ideas about how could we use these instruments in combination to tackle novel questions, and are there alternative ways to use these instruments that would benefit exoplanet science? So maybe I'll get the discussion rolling here. So Dimitri mentioned that one attribute of high spec is that it's very complementary to KPF for young star forming regions and for red stars, right? And the reason for that is that with young stars, stellar activity can impart a pretty significant radial velocity signal at optical wavelengths, but that seems like it might be mitigated at redder wavelengths based on sort of the latest results. So hopefully the precision at redder wavelengths would be better matched by the actual Doppler reflex of the star and less dependent on magnetic activity. I guess do we have a sense yet from other near-infrared spectrographs and their performance on young stars, what kind of performance we might expect for high spec on, I don't know, stars of like 10 million years or something?
I think Chas could take that one because he's done some work on it.
Yeah, I mean, there's a couple of factors that play in, both on the instrument side, the Earth's atmosphere side, and on the star side. You know, we've clearly seen demonstrated many times that at the many meters per second level, young stars are very active at visible wavelengths, and you gain factors of, 3 perhaps as you go, say, into H-band. I mean, John Kralls, Crockett, Lisa Prado, a number of people have all looked at that. We've used IRD and compared that to high res, and again we see a reduction in the stellar activity level, which is significant. So purely an increase in instrument sensitivity doesn't help you with that. The downsides of the IR instruments, which are still being worked, is the Earth's atmosphere is, very friendly for people, very unfriendly for near-infrared observations. And, the limits we may hit may be, at the 1 meter per second level, something like that, with some pretty aggressive work that quite a few people are starting to do to help take out the effects of the Earth's atmosphere. But that's certainly going to be something to mitigate against. And then third, everyone's still essentially debugging their infrared spectrometers. We don't really know what those final limits are. The Carmenas guys are complaining that their detectors, and these can be very batch specific, are limiting them to something like 5 meters per second. We don't really know yet. So this is still a pretty active research area. I would say the ground hotter than M3 or M4 belongs to Andrew, and we don't really yet know about the later spectral types, except in the area of stellar activity where that extra factor of 3 may work to your advantage.
So one thing I'll add, so we've learned from the Carmenas instrument that chromatic radio velocities can be powerful, so measuring in the visible and in the near infrared. With Carmenas, it's been challenging for a few reasons. Chaz alluded to some of the instrumental challenges. There were also challenges with the thermal control system on the infrared side of Carmenas in particular. So I'm hopeful that high spec will have better performance there. And so the sort of cross wavelength capabilities would really be enhanced. We could do simultaneous KPF and high spec measurements sort of expensively right now, or in a couple of years, by monopolizing Keck 1 and Keck 2. But maybe an even a better possibility is to, and this would be beyond the scope of what we currently have funded, but to find a fiber injection unit that can feed light to both instruments simultaneously. We'd have to, I think we might end up having to kind of chip away at the bandpass of one of the instruments to get enough light to feed the AO system so that we could actually get enough light into high spec. But I think that would be really powerful. it would also overcome another challenge that Carminus has had, which is that they're really photon starved in the infrared side when they want to do optical plus infrared measurements and get good velocities from both. So I think the aperture of Keck feeding both of these instruments could be a really great combo.
Yeah, I agree. And there may be a simpler solution, just replacing your flip mirror with a dichroic, sending visible light to KPF on Keck 2, and then letting the infrared light go through the system. And if we use the infrared wavefront sensor, there is a way to divide the light smartly between the wavefront sensor and the instrument itself. So we would have to sacrifice a little bit of one band, but depending on the magnitude of the object, that may work.
And J-band actually has relatively modest spectral information compared to the longer wavelengths, particularly for the cool stars. So you could sacrifice J to run the AO system, for example.
Right.
Yeah.
Another thing we hope is that Parvi, which has been basically, dead in the water for the last 9 months due to COVID, when it comes back online, which we hope, early next year, will be highly stable. I mean, we've already demonstrated stability at the millikelvin level internally, and it's a very compact system. It's, about the size of a microwave oven, compared to the size of a small Volkswagen for something like Spiro or something like that.
Substantially better thermal stability than a microwave oven.
Yeah, exactly. Size only. But that small size really lets you focus in on stabilizing and minimizing gradients in space and time over the whole instrument. So I think with Parvi, we should be able to demonstrate, what are the other instrumental limitations? And it could be the detectors will be a problem, in which case, we may have to design instruments with, slightly more sampling per resolution element, for example, to get rid of some of the flat fielding errors. I mean, this is why I say we're still very much in an experimental phase with how to do these things. An upside is that laser frequency combs are much easier to make work at these wavelengths than they are at the visible. And so we really have telecom-based LFCs that you sort of piece them together and they work.
Yeah.
Maybe one thing for folks to think about going forward is to maximize the RV capabilities of high spec. I think there needs to be increased effort developing activity indicators in the infrared. This is a somewhat well-developed field in the visible, I think less so in the infrared. So finding lines that are particularly sensitive, finding machine learning approaches that use the whole spectrum, I think would be something that could really push this forward on the IR side.
Yeah, we've talked about a couple with Trevor David, for example, had some ideas, and Parvi was supposed to be plowing through stars doing all this, of course, this semester, and we're on hold. But yeah, no, that's absolutely a goal that we're talking about.
On the sort of, I want to eventually move like a little bit broader than just precision RVs, but one more point on this optical near IR comparison. One of the issues that some spectrographs, including both IRD on Subaru and Spuru on CFHT, have had is this issue of persistence in their detectors. How are we going to get around that?
It is certainly an issue. It is, again, a individual detector issue, with later batches being typically better. These devices are still pretty bespoke devices. There's also variation within individual devices as to what temperature you operate them at can affect the persistence as well. So there's some, again, work we have to do to understand that better.
So I would like to add, so in the high spec team, our key collaborators are University of Montreal, so René Doyon, Etienne Artigot, who are some of the architects of Spuru, and the latest news is that they seem to be able to deal with persistence pretty well with Spuru. So I think it's a combination of understanding the detector and how to expose it properly, but also some, if I understand correctly, some forward model of the effect. So it seems that at the moment it's not an issue for them anymore.
So I had a question for somebody on the high-spec team. One of the talks this morning by James Kirk was on near-spec observations of helium-10 as a probe of evaporating atmospheres. And one of the takeaways that I had from that talk was that near-spec is currently the premier instrument because of its, well, mostly at the aperture, but it seems like there's some opportunities for improvement with spectral resolution and perhaps efficiency too. So I wonder if anyone on the near-spec team has quantified the performance for those kinds of measurements.
So talking about transit spectroscopy in general, so it seems like it's going to be one of the key, if not the flagship science kits for high spec. So Bjorn Benicki at University of Montreal started to do a lot of simulations showing that high spec will be one of the best, if not the best, machine for transit spectroscopy. And helium 1 is going to be one of the key strength, key science for high spec. We haven't really looked at in direct comparison with NIRSpec right now, so that's something we could add to the list of simulations.
Cool. We've talked a lot about high spec and comparisons between it and KPF and near IR versus optical precision RVs in general. But we also have, as Dimitri was discussing, these incredible new imaging capabilities with KPIC and NERC2. So one question that I had is, KPIC and NERC2 are on Keck 2, HiRISE is on Keck 1, KPF will also be on Keck 1. So is there some possible synergy for using these instruments, potentially even simultaneously, to characterize individual systems? What kinds of systems would those be? What kinds of observations would we want to do? Is there some cool science that we haven't thought of yet that we should be doing?
I mean, I just want to start the discussion, but I want to I've talked too much already. I want the others to get a chance to talk as well. So, but I think it's clear that the field of direct imaging and direct spectroscopy is morphing into something new, where combination of techniques is the way to go. So blind direct imaging surveys, I think, are going to be a thing of the past, and I think the future into combined RV astrometry with Gaia and direct imaging or direct spectroscopy. And I think there is great power in combining these techniques, and now we are slowly but surely chipping away in the parameter space, where at some point we'll have a large overlap between we can detect with RV astrometry and take pictures and spectra directly. So there are a few examples already, but I think we're going to have many more of those in the future. So I think synergistic studies are the way of the future.
And just to add to that, I think we're trying with KPIC to push our sensitivity to older stars. Improve our sensitivities at L and M band, where we can access planets around older stars. If RVs can do better on younger stars, maybe we can find there's a part of parameter space in which we actually overlap on the same stars. That would be pretty awesome.
Yeah, that's definitely a direction that I'd like to see the field go. I wonder if there are already systems for which we can accomplish this, like AUMIC or Beta PIC.
Yeah, so I think you mentioned maybe the handful of systems that maybe we could try to do. Unfortunately, like the AUMIC planets are too close in to be spatially resolved. Certainly beta pick is very interesting. Like Dimitri said, epsilon A or Donny B, but we're still counting on one hand.
Hopefully Gaia will give us a lot more. I think there was a poster from Thane Curry about that, so maybe Thane is around, you can say a few words about that.
Does somebody, maybe Andy, want to talk about how scales fits in to this landscape?
Sure. So scales, I guess, Steph Salem gave a talk this morning, which probably many of you saw. And then we're in the infrared spectroscopy breakout session tomorrow, so you can hear more about it there too. So scales, to remind you, it's a 2 to 5 micron integral field spectrograph. And so while most of the exoplanet imaging instruments in the world, the integral field spectrographs all work in the near infrared, like JHK. But many of you will note that NERC2 has discovered a lot of exoplanets by looking at longer wavelengths, L and M band. And so we're sort of combining the two best methods for imaging and detecting new exoplanets with direct imaging. So that's integral field spectroscopy and the thermal infrared with coronography. So yeah, that's one of the things that makes us different. We work at longer wavelengths. The other thing that makes us different is that we're going to have a medium resolution spectroscopy mode. And you might think starting to get complex out there with instruments that work at low resolution spectroscopy, medium resolution, and high resolution spectroscopy. But they're actually sensitive to really different things when you're taking a spectrum of an exoplanet. So low resolution, you're mostly looking at the continuum. High resolution, you're mostly looking at individual lines. Medium resolution kind of gets you in the middle where you can get the continuum and the individual lines. So that's what we're going for there. I think it's complementary to a lot of these instruments. I don't really have, it doesn't have a radial velocity or transient case necessarily. It's pretty purely for direct imaging as far as the exoplanet science case goes. Non-exoplanet science case is much broader.
Yeah, I personally see scales as a successor of NERC2. I think NERC2 is getting very old, and I think it's still going strong. Still a lot of potential, but in 5 years from now, who knows if this instrument is still going to work. And I think scales will provide most, if not all, of the capabilities of NERC2 and more, a lot more.
Yeah, so for those of you who haven't done direct imaging with integral field spectroscopy, you get a huge contrast improvement just from using integral field spectroscopy for a couple of reasons. One is that the speckles move outwards with lambda over d, and so you can distinguish them from planets. And the other reason is that the SEDs of planets are just completely different than the SEDs of stars, and so it makes it easier to distinguish, and you can do things like matched filtering. So we think we get, depending on the temperature of the planet, between 1 and 3 magnitudes of improvement by doing integral field spectroscopy instead of imaging with NERC2.
That's a fantastic improvement.
So I should also mention that we are currently working on upgrading the Keck 2 high order deformable mirror to a high order deformable mirror, so to enable extreme adaptive optic system at Keck fully for the first time, which will benefit these future instruments, all of them. We're relying on adaptive optics, so high spec will benefit from it. Scales will definitely benefit from it, but they will also enable diffraction limited imaging in the visible, which is a new capability for Keck. It's something that the Arizona group has been doing for a while on McGill sphere as a visible light imager and polarimeter, but combining laser guide stereo, infrared waveform sensing with visible light imaging is something that could be truly unique to Keck. So if you have ideas on how to use these future capabilities, you should contact either me or Mike Gerard on the line. So there's a working group currently looking into making these upgrades possible.
Yeah, one thing, Dimitri, we should mention about high spec is Quinn Konopacki is leading sort of a science team effort with you know, quite a few people engaged from the community, both on the exoplanet side, but also non-exoplanet science. So to the extent that people would like to get engaged, contacting either Dimitri or Quinn is the right way to go.
Dimitri, question about upgrading the Keck 2 deformable mirror. So I think one of the original goals of the Keck Observatory was to do interferometry at optical wavelengths. Would this be part of the path toward that? And if so, what are the other main hurdles?
So I think KPF is gonna put an end to our interferometry ambitions at Keck for good, except if we can actually use fibers. But you know, as you know, KPF will be in the tunnels, so former interferometer tunnels. But I think
We are glass.
Yeah, I'm sorry to report that the long delay lines in the Keck basement were ripped up a couple weeks ago. So Keck's interferometer days are in the past, at least with that hardware.
Yeah, so I think there are other ways to transport the light via optical fibers. That's possible. That's been done before.
Yeah, you still need to equalize the path lengths.
Right, yes. So we'll have to find other ways to do that.
Heterodyne. H nu over K is not your friend.
Or we drill a hole in the middle of KPF. I don't know if you can do that.
No.
So I should mention that Peter Wisniewicz and Sam Raglan are on the line. And if you have any questions about the ongoing upgrades to the Keck adaptive optic systems, they are the right people to talk to.
There is a session, this is Peter, there is a session, breakout session tomorrow on KEK-AO and the future of KEK-AO. So we'll certainly be talking about these items tomorrow. But in terms of improving Exoplanet, I'd say, you know, it's the high order DM that's going to help us the most on Keck 1.
Keck 2.
Sorry, Keck 2. On Keck 1, I think you will also be helped by Kappa. And you know, if you want to use Osiris or hopefully Liger longer term. Actually, maybe Sam could give a little bit of an update. I mean, he's been working with you, Dimitri, Mike Bottom, Becky, Jensen Clem, on some other improvements in terms of speckle nulling and predictive waveform control, that kind of stuff. You want to say anything about that?
Sure. Yeah. We have a kind of parallel project in parallel with the KPIC, that is to understand and minimize the residual wavefront errors on a different levels. This includes doing predictive wavefront control, that is through a project that Becky is the PI. And more recently, we got funding, NSF funding for, again, multiple small projects that includes predictive wavefront control and speckle nulling. That is, Mike Bottom is the PI, and Becky is also PI, and I'm co-PI on that. In addition to speckle nulling, we have schemes to improve the phasing of the segments. Again, using different approaches. I've been doing a couple of procedures like using phase retrieval approaches. And as a part of KPIC, we have a Zernick mask now. So that adds another layer for us to sense any residual segment piston errors coming from the Keck telescopes, and hopefully be able to improve the phasing. Okay. And there are other small projects as well, but all along that same line trying to either understand the residual wavefront error or apply corrections to either to the telescope or to the AO system.
I just want to do a quick time check. How much longer do we have in this session?
I think 2 minutes.
Okay.
I think we've got until 2:30.
Oh, cool.
Oh, wow. Okay.
We probably don't want to let people out exactly at the start of the next thing, but
Yeah.
that's the case.
Yeah, so what do folks want to do? Do we want to sort of keep going with sort of listing statuses of other instruments that might help exoplanet science and their capabilities? Do we want to brainstorm more about projects that we could do with multiple different instruments or possible complete new techniques for studying exoplanets with these new instruments? Or do people want to call it a day?
Lauren, could I ask a question? This is Peter. So
Yeah, go for it.
part of the high order DM is we're considering whether we want to have a visible science instrument. And we probably struggle to fit anything significant into our proposal. But longer term, what visible science instrument would the community be interested in? Is it spectroscopy? Is it an IFU? Is it an imager? Where is the interest?
How visible are we talking?
Well, I think it's, I think we're probably lucky to get to 800 nanometers with just the high order DM. But if you go on very bright targets, fifth magnitude or something like that, I think then you can be starting to think of going to 600 nanometers.
I guess, Peter, how would you compare, what your estimates are for Keck with what Laird's been able to do with, MagXAO?
Right, and that's a good point, Chaz. I mean, he's been able to do great things down to 600 nanometers on very bright targets, right? And that's basically what we'd be providing with the high order DM. We'd have the same aperture size, basically. We'll have 20 centimeter sub apertures, and that's what MagAO has. So if we can get rid of some of the other residual effects that maybe MagAO is not suffering from, like primary mirror phasing, there's no reason we shouldn't be able to achieve those kinds of levels. And to throw something else into the mix, I don't know if John Mather's still on the call here, but we're also talking about ORCAS, which is an orbiting satellite that provides a zeroth magnitude star. You could always have a bright star potentially. So there's lots of ideas out there. And in that case, we should be able to push down to the 600 nanometer kind of thing.
Yes, I'm on.
Oh, you're muted, John.
Yeah, this is John Mather. I've been working with Peter for a while on this topic. And yes, I think there are lots of possibilities that we could support providing a guide star wherever you need it, whenever you need it. But it does take a lot of planning and work. So if we can build the AO system to go with it, then it gets pretty interesting.
So back to the, maybe to the question I was asking, which is, what visible science instrument would best serve exoplanet science?
I wonder if this is a failure of my imagination, but I'm having trouble seeing what science one would do with visible imaging that one would not do better with infrared imaging.
Well, yeah, if you look at, what they're able to do on things like PDS 70 and so on. You know, they're seeing H alpha in protoplanets. Now, we're also trying to do this with some of the infrared hydrogen lines. But, you know, H alphas, everyone's used to H alpha. So you could certainly imagine some imaging things that you'd like to do there with enough spectroscopy to isolate the line. And then, you know, very good imaging scale. So there could be a few cases, they might be pretty specialized.
You could also do albedo studies of imaged planets and extending down as far as you can go into the optical probes, the properties of the clouds.
And of course you get, I mean, as you go to shorter wavelengths, you're going to get higher angular resolution. So you can potentially get closer to the primary star. And another thing to consider is precursor science for TMT, you know, or precursor demonstrations for TMT where they'll have even a higher angular resolution, where you can potentially detect Earth, you know, an Earth shine with a TMT.
Yeah, I wonder if there would be any benefit to feeding KPF with diffraction limited beams, so benefiting from the angular resolution of AO, so in closed binaries, for instance. So the angular resolution in the visible would be 10, 15 milliarcs again or so you could really isolate the signal. The throughput wouldn't be great, but I think on bright binaries that would be interesting.
Yeah, I mean, the other thing you could do, we've explored this in this Extreme Precision Radial Velocity Initiative, was to take advantage of, if you can feed it a fraction limited beam at visible wavelengths, you know, say down to, you know, 500 nanometers or a little bit north of there, then you can build something that again is the size of a microwave oven, but has a resolution of 300,000. You know, and Andrew's worked heroically, you know, with slicing and everything to make KPF credible, you know, buildable at the resolution they have. If it wanted to have 3 times the resolution, that's starting to get tough. So if you could feed a R of 300,000 or 400,000 instrument and work only on the very brightest stars, and that's what the EPRV initiative is about, you know, that becomes something you could think about in the long run.
Another science application that has been sort of tossed around, I don't think anyone's actually built anything, is an ultra high resolution spectrometer, maybe focused on the oxygen A and B bands, to do combined light spectroscopy of planet plus star. And you have to go to extremely high resolution, like a couple 100,000, and it keeps getting better if you go even higher. And the idea is that the Earth's A and B band lines just look like a couple picket fences that are saturated in many of the lines. But then you get little absorption lines in between from the planet that kind of move back and forth. And they should have a width determined by the broadening profile of the planet, which can be extremely small because it's just rotational broadening. So you keep winning with resolution up to some point up in the several 100,000 resolution regime. Such an instrument is probably a kind of specialized thing, and maybe you want to make it, you know, as high as efficiency as you can, so you focus on just those lines. But if we got a compelling pale blue dot and we really want to take a great spectrum of it, that's the kind of thing that might be interesting.
Yeah, I think the CFA guys, Andy St. Georgi, has, you know, thought about it. I think there's at least 1 or 2 papers on that. And if you're diffraction limited, it becomes, again, quite a compact device that you can stabilize and do all the things that come with having something small. And I think that really would require, Peter, I think, you know, really getting down into the, certainly into the red part of the spectrum.
I have a dumb question, which is that we're throwing around the term diffraction limited a lot. But in reality, even the best AO systems have some PSF that's not perfect. So how good do we really think we can do? Would it be better than space?
Well, we already do better than space at the longer wavelengths, right? Where we are close to diffraction limiting, right? So at K, we are getting 45, 50 milliarcsecond images. So as you go to the shorter wavelengths, we not only need to, well, actually our tip tilt residual is still actually relatively small. So it's, the key is getting a higher strahl. But if we can maintain that few milliarcsecond kind of tip tilt as we go into the visible, then we just need to pump energy into the ore. So,
Yeah. I mean, if space does LUVOIR, we can all go home. If space does HABEX, there's still a lot of room to do stuff. I mean, 15 meters in space is awfully good.
So there's something missing here that is relatively new and may come sooner rather than later. Is that Chaz and Stephanie Leffer have been working on trying to bring an infrared laser frequency comb to Keck in a relatively short term. That would be to work with NeurSpec first, but it could provide a solid foundation for a calibration unit for high spec as well. I don't know, Chaz, if you want to say a few words about that.
Yeah, we basically would take the system we've developed for Parvi at Palomar and bring it to Keck, and it would also require some modifications to KPIC, both on the input from the AO system and then to the input to NeurSpec. But I think there's certainly interest to do that, and Hilton and John have been very supportive, so we're hoping that that we may be able to find some funding for that in the next couple of months. We actually proposed this before KPIC was a thing about 5 or 6 years ago for NeurSpec into the NSF, and got 2 excellents, 1 very good, and no money. So we could have actually been way far ahead already, but this is just another shot to do it. And I think if the end goal were NeurSpec, NeurSpec is not the be-all and end-all, RV machine, just because the resolution is now by modern standards pretty low at 35,000. But what you do get with the LFC is you get a great set of samples of your line spread function across each and every order. And you can use that to, for example, to help all these cross-correlation function spectroscopy experiments really depend on having a very stable line spread function. And so you'd have an exquisite estimator of that. You'd certainly be able to do few meter per second PRV for, again, the specialized objects for which that's the case. Probably not in a survey mode, but for specific objects where you want to do a Rossiter-McLaughlin experiment, for example, where you need the instantaneous sensitivity of a large aperture and the stability at a few meters per second on a red object or an active object. I think there'll be some interesting cases for NeurSpec, and then as high spec comes along, you get all these advantages with a much more highly optimized instrument.
Yeah, that sounds great. So do we have funding yet for the laser frequency comb? When is it coming?
Watch your emails. Yeah, I think we'll know in the next couple of months if some avenues we're pursuing work out. I think Keck's been very active. Some people at Caltech have been very active. So we're hopeful, but hopefully the stock market stays high and rich people still want to give us some money. But technically, it could go quite quickly. I mean, that's the advantage of it. It's telecom parts. You go to Edmund Scientific, you order them, you put them together with a smart grad student, and then you do the mods to KPIC, and we could be operating pretty quickly. We've already tested essentially this exact comb 3 or 4 years ago with some articles that we described this all in Nature Communications and Nature Photonics. So the installation is pretty straightforward.
Sounds fantastic.
And there goes more of the interferometer.
It's pretty small stuff, Peter. But we'll probably steal one of your optical benches. Yeah. Peter, we tried so hard. We did so well. And to see VLTI and gravity doing everything it's doing kills me every day.
Hold back the tears.
Yeah. And steal the parts.
Well, or maybe just convince Elon Musk that Starlink 2.0 should actually just be an interferometer.
Right.
Maybe that's the path to success. Okay, what else should we talk about? Going back to our main questions, what new instruments are there? We talked about a lot of new instruments and the ways that they're designed to enhance exoplanet science. We've talked a lot about some novel questions, pushing toward young stars, pushing in terms of if we could do diffraction limited imaging at visible wavelengths, how would that open up exoplanet science? And wow, I learned a lot that I didn't realize we're missing in terms of both imaging and actually putting a spectrograph behind an AO system at visible wavelengths. We could really do a lot with that. I guess, right, this is sort of the tricky one. What are the ways to use our instruments that we aren't thinking of yet, right? I guess one of my favorite examples for this is the sort of spectroscopic binary and or transmission spectroscopy type use of high resolution spectrographs that was pioneered on CryRes. Right? This idea that you've got these close in hot Jupiters and they have spectral lines and you can map out the phases of those lines. It's pretty nifty. Are there other opportunities for that kind of alternative science that will emerge as the result of these technical innovations we're discussing?
Yeah,
Yes.
so you described one of what I consider is the primary science case for high spec. So it's exactly doing that. And here again, you need very high resolution because you rely on the radial, on the planetary radial velocity during the transit, which is of the order of a few kilometers per second in the most interesting cases. So you need very high spectral resolution to be able to disentangle between the planet lines and the tellurics. So I think there is a lot to be done there. I mean, the current estimate of number of targets that can be addressed with this technique with an optimized instrument is in the hundreds now. That's a recent simulation by Bjorn Benicki for high spec. So I think there is great potential in that technique when we have an instrument that is optimized for that.
Yeah, and in fact, they don't even have to be transiting. I mean, the nice thing is they're still moving even if they're not transiting. So it opens up, again, the broader sample of objects than just the transit sample.
Right.
Yeah, that phase coverage seems so critical. So going back to Dimitri's slide on this, of course, I love the figure with planet mass and semi-major axis. So, right, this is, maybe not quite yet tuned up for the exact specifications of high spec, but one thing that sort of bugs me right now about the SB2 characterization of planets is it's kind of only applicable to hot Jupiters, because as you get smaller and smaller planets or planets further and further from their stars, the spectral, right, the fraction of the light that's the spectrum of the planet diminishes. So, I'm curious, right? There are these ultra short period planets that are probably rocky, or maybe have some stuff other than rock in them, things like 55 Cancri E. So will high spec be suited to studying ultra short period small planets? And then on the flip side, if you want to push in the large but cold direction, how far out could we get?
Yeah, that's a great question. So that's the kind of questions we are trying to address right now. So what is the limit given the resolution? So we need to reach a compromise on the instrumental resolution. But so for the reason you mentioned, the planets further out have smaller velocity shifts, and so that's where the resolution is critical. So the transit people in our team are really pushing for even higher resolution than 100,000, but we have to reach a compromise here. We have a limited number of pixels on the detector, and we think 100,000 is probably a good trade-off resolution. So we started to simulate cases like TRAPPIST-1, I think TRAPPIST-1E, and it's on the edge of detectability with something like high spec. You will need to pile up a lot of transits, but it could be potentially done if we decide to spend the time. So that gives you a upper limit on what we can do.
Yeah, I mean, and look, in some of these things, as you go colder, as you go smaller, you just need more sensitivity. And, we're hoping that we can take high spec, as you see here with the 2 microwave ovens, and eventually move them over to TMT. Because once the light gets in the fiber, the spectrometers don't care how the light got in the fiber. It's either a 5-meter telescope at Palomar, or it's 10 meters at Keck, or it's 30 meters at TMT. The microwave oven stays the same. And there I think you get another big jump up that lets you push to smaller and colder.
Yeah, certainly in the near term, if high spec could accomplish either sort of warm Jupiters or hot ultra short period planets, that would really open up a lot of new science, because there are just so many planets in both of those portions of phase space.
I think the warm Neptunes and certainly warm Saturns are going to be quite credible with high spec.
But the small ones are the most fun.
Yeah. We've been waiting for 25 years to get the Earth, and maybe another 25, but we'll get there. The extragalactic people didn't get the Z of 15. It took them a long time. But we'll learn a huge amount about how to do this science, with high spec on Keck, that really lays the groundwork for what we then get to do with TMT.
All right, so I feel like a few of us have really dominated this discussion. So I just want to really open it up again and make sure that other people, especially students, have an opportunity to chime in, ask questions, say, what exoplanet science goals are important to you. We'd love to hear from you too.
Yeah, I guess I have a naive question about the younger systems, going back to like the directly emitted planets and how it's hard to get RV of their stars. Is something like high spec capable of getting the radial velocity of the planet itself, or maybe the brightest planets? And what is the precision of that RV?
Great question, Jerry. So, now, as you know, we can get RVs of directly imaged planets right now, but the limitation is not so much the spectral resolution of the spectrograph you use, but the signal to noise ratio of the detection of the planet. So I want to hear it from other people. I want to do all the talking, and I don't know if JB or Jason want to chime in on this and tell us what the state of the art is on measuring planetary RVs directly.
Jerry, I kind of missed can you repeat your question exactly?
Yeah, I just mean like to better characterize the orbits and masses of young planets.
Yeah, so I mean, I think the one thing I was going to say is, like you pointed out about surprisingly right now, it's easier for us to compute to get the radial velocity of the planets than it is to get the radial velocity of the stars they orbit. Because most of the directly imaged planets are around high mass stars, which have just like a couple hydrogen lines that are very broad and usually pretty big V sin I's. So even though we can get sub-kilometer per second precision on the RV of the planets, we usually don't get that good of an RV of the star, so it's not that helpful. It's not, so there, I mean, it doesn't mean it's not helpful at all. I mean, but it's limited.
Yeah, I guess I was most curious, like if we can get to better precision than kilometer per second for the planets with high spec or new instruments.
Yeah.
Yeah. Yeah, except for the hot stars, the information content in the near infrared is pretty woeful. It's not great in the visible, but it's doubly woeful in the infrared. And also the lines are really broad because the hot stars are rotating pretty rapidly.
I'll just chime in here to clarify that in order to actually get the RV of the planet with something like high spec, you have to be able to resolve the light from the planet from that of the star in imaging first. So for some systems like Beta Pictoris or whatever, where you can actually see the planet, that's definitely going to be possible. But then there are others that we talked about earlier, like AUMIC, where the planets are still just too close to the star for the resolution limits. So in that case, we would have to measure the RV of the star to infer the motion of the planet.
Yeah, that makes sense. I was just wondering about the directly imaged planets, I guess. Yeah.
Yeah, I mean, for the directly imaged planets, we're signal to noise limited in our radial velocity, so having high spec will drastically improve the signal to noise of our detections, which will improve the radial velocities of the planets by a lot.
Cool. Yeah, because like the planets move faster than the star, so it should help to look at the planets, if possible.
Yeah, certainly. It helps constrain the orbit. Unfortunately, getting the planetary RV does not give you the planet's mass. You actually only constrain the star's mass that way. So you only get the orbit from the RV.
But you could look for exomoons by getting RVs of the planet.
That's right.
And we'll get there.
Lauren, I could say a couple words about a new interferometric mode that we're working on for the OSIRIS imager.
Yeah,
sorry,
that would be great.
I showed up late, so
well, you're most welcome.
Yeah, so is it okay if I share my screen just to throw a slide up?
Yeah, go for it. Here,
Okay.
I'll stop sharing.
Thank you. Cool. Yeah, so something that I've been working on with Mike Fitzgerald and some other folks is creating a holographic aperture masking mode for OSIRIS. And so this might be interesting to some folks because it can be kind of complementary to more traditional direct imaging. So you use an aperture mask to turn your field aperture into an array of subapertures. And HAM allows you to multiplex your mask using liquid crystal coded optics. So you can create multiple PSFs in the focal plane to get a little bit more phase information and some kind of cheap low resolution wavelength coverage. So that's what this figure shows, is just a monochromatic PSF and then a 30% bandwidth PSF for the mask that's in OSIRIS. And so with this mode, you can get contrast of something like 6 magnitudes in K-band at lambda over D, and also like a small amount of spectral resolution. So this is just an example of some test data we took at 1.6 microns, where we observed a known binary to like demonstrate that that this mode is working. So it might be something some folks are interested in. I figured I could take a second to mention it.
So, yeah, this is cool. Can you remind me what's the wavelength coverage that this operates at, and what was the resolution?
Yeah, so this is JHK, and then do you mean spatial or angular resolution?
And spectral.
Yeah. So the angular resolution, you get decent contrast down to around lambda over D, but you can still detect low contrast companions at like half lambda over D. So K-band, the resolution is about 20 to 40 milliarc seconds. And then this plot kind of gives you an idea of the spectral resolution. All of these wavelength points aren't necessarily independent, so I would say it's a little bit worse than what you're seeing here. So definitely low, low resolution, but like better than broadband.
How do you envision this complementing, for instance, the instruments like scales that are coming in the future, which I think is also sort of a low resolution, high throughput instrument?
Yeah, so this is definitely lower resolution than the low res scales modes. The wavelength range that this optic operates over is different from scales, but that's not like a requirement for using ham. So yeah, I think this could be like a good option for observing something where you don't care about having R of like 50 spectral resolution, but you do care about really good angular resolution and like having some I don't know, R of some low spectral spectral resolution constraints on whatever you're looking at. Yeah.
That's super cool. It's like there's an instrument for every like combination of technical settings that a person could want. Okay, I think it is time to wrap up now. I guess I'll just close by saying thank you to everyone who contributed slides and asked questions. I'm gonna leave these, I've been taking notes in the Google Doc the whole time. If I've like typed something incorrectly or whatever, feel free to fix it. My hope is that this will continue to be a document for reference, or maybe even a living document where we can keep sort of keep each other up to speed on what are all the options for exoplanet instruments at Keck, and think creatively about what new science we can do in the future. So thank you everyone for coming, and see you back in the main session.
Thanks, Lauren.
Thank you.
Thank you.
Thanks, Lauren. Bye-bye.